Hey kids, ready for some more Stokes theorem? And we're going to work with some more problems. The homework that you did with the previous video asked you to do, right, asked you to evaluate the surface integral. And I said to do the, using Stokes, then I wanted you to do the line integral. So here we're going to do some examples where I ask you to find the line integral. But we're going to use Stokes to say, I don't want to do the line integral. I'm going to do the surface integral instead. So look at this surface. I have a plane z equals y, and they're giving me the x and y boundaries. And they're giving me the vector field that goes all swirling all around here. But look at my line integral. That's not a smooth curve. So in order to actually do the full line integral, I would have to compute 4 different line integrals and add them up. I don't think I want to do that. So I'm going to say no to the line integral, and I would much rather do the surface integral. So stoked, right? So the surface integral, well, what am I doing with the surface? I don't really have a 3D surface. Well, remember the whole idea of the hat. Right? The hat on top of there. So the whole idea of the hat is that it is just the boundary because of this equality. I can choose any 3D surface, but I really am talking, if I'm going to pick any 3D surface, why wouldn't I just choose the surface of the plane, the flat surface? And then Stokes equality lets me say that the total infinitesimal circulation all around the inside of this surface is equal to the circulation on the boundary. Now I highlighted clockwise because this means that my normals are pointing down instead of up. Notice that my normal is not, right? This isn't on a flat, it's not flat on one of my coordinate planes, right? It's not flat on the XY, flat on the YZ, or flat on the XZ. So my normal isn't just I can't kind of cheat with my normal and consider, right, Z has no height. So this time, instead of, I've highlighted this formula before where I've made sure I want you to realize that you are dotting the curl with the normal, right, which is what we're doing here, the circulation around each one of these points and sum them all up. That I'm going to kind of use the Green's theorem adaptation, where I wrap the normal up into here, right? So I have my vector field dotted here, where the curl of F is a vector. And I'm wrapping the normal up in here, and then I can use, right, the surface area can be 2D over the region, over a region, right? So as long as these values, P, Q, and R, come from calculating curl. And then these are the partials. This is my dot product with the partials of what? My surface. Right, surface in terms of X and Y. So the condition, though, of using this is that I'm got an orientation where using the set of all vectors that are pointing up, and I'm not. So because I'm going to use this, assuming that I'm using the normals that are all pointing up, I'm going to make sure that I negatize my answer when I'm done. Because the set of all normals traveling around this clockwise using the right-hand rule would be pointing down. All right, so let's calculate our curl. And when I do that, I get 2yx minus 0. And I get y squared minus 0. And then I get, what, partial with respect to x is going to be 4y cubed minus partial x squared with respect to z, 0. So here is my P, Q, and R. So my surface integral, curl f dot n, going to turn in using the Green's kind of extension here. The opposite of P times the partial of my surface with respect to x. What's the partial of the surface with respect to x? Hello. That's nice, right? The opposite of Q, so my Q was negative y squared, so positive y squared, times the partial of my surface with respect to y, plus just my r. Now, what am I going to turn my dA into? Right, notice everything is in terms of y. I have my bounds, don't I? My bounds are just constants. So as I do dy dx, because both of these are in terms of y, then that means that my x values 0 and 1 go on the outside, and my y values 0 and 3 go on the inside. And I trust that you can integrate that, do the double integral. When I do this double integral, though, I get an evaluated, I get 90. But be careful. What's true about your orientation? Negative, right? You got to negatize your answer because of the row you were rotating in a clockwise direction around this boundary. All right, pretty cool. Let's do another one. All right, so I have a closed curve, C, a closed curve oriented counterclockwise, yay. But look at this. Why do you think I have thumbs down? The intersection of the cylinder, here's the cylinder, and this hemisphere. And they want me to evaluate this line integral. Ew. Now it's already been dot product, right? Ew. Parametrize, huh? What? Ew. So what do you think I want to do with this? I'm counterclockwise, so I don't have worries about going from the line integral, choose the surface integral. So stoked. Gonna wrap this up so that I'm actually gonna do this version. Right? So let's do our curl. If you want to pause the video, see if you get the same thing I do. Right? Do you see where I got those from? This was the vector field already dotted with dx, dy, dz, which is your ds. So when I end up with doing that, I get a really nice curl, right? Can you see it? What do you get? Right, for my first one, I get 0, 0, and 1. So there's my P, Q, and R. And now where's my surface? Well, what is that surface, huh? Right, what do I have with my surface? I don't have to worry about them, do I? Do I have to worry about calculating the surface of the partials of the surface? Why not? Hello? So who cares? So I'm going to end up with -0 times I don't care what, which is going to be 0. And then minus q, which is 0 times the partial of my surface, who cares? Plus, minus 0, whatever. And then just plus r. Now, what is the projection of that surface on the 2D projection of this on the 2D plane? Didn't do a very good job of, right? What's the projection of that as you go down? Isn't this just the area of a circle with a radius of what? Right? Very nice. All right, that's it. We'll do some more examples together in class as we practice our Stokes theorem. Remember, so today there's only 2 homework assignments that go with this video, and they are asking you to do the line. You say, no, I'm so stoked, I can do the surface integral instead. All right, I will see you in our next live session.